Okay, welcome to this video. The video is about spatial joint improvements for PostGIS in the UAV domain. This is being recorded for a graduate level database course at Nova Southeastern University. And today, as I said, we'll be talking about spatial joint improvements in PostGIS. The motivating factor here is basically that unmanned aerial vehicles, UAVs that is, and unmanned aircraft systems, UASs, are generating some really great flight data. So here's an example on the right. I also thought I'd play a quick video showing some sample flight data that's been recorded for a particular DJI Phantom test flight. This test flight was done by DJI Phantom, which is a commercial, retail-based drone that you can buy, at Best Buy or something like that. And this is just standard footage that you can record, on your own. It's not, very advanced or anything like that. So what we'd like to be able to do is take advantage of this kind of data. So that's the main thing that we'll be looking at today. And so the problem is that there's relatively little available in terms of open source solutions to process this data into photogrammetric data that can actually be used. So what you need to be able to do in order to make use of this data is you need to be able to actually turn this into a model of some sort of representation that can be used for the particular UAV that's in question. So you need to be able to know that, for example, this is a cylinder or something like that, or in the case of this video, these are roads, these are buildings. If you're flying too low here, you would hit the building. That's particularly important for takeoff, for example. So if you're taking off, so for example, in this direction here, there's a building there, you would need to actually turn before you hit the building. All that information needs to be represented somehow, and so spatial joins become really important here because there'll be information that's returned from the video capture, as well as information that is gleaned from things like Google Maps and other mapping applications. So there's going to be plenty of times where we need to actually join this data up with other data to make a representation of the world. Specifically, this research is going to take advantage of something called touch, which is an algorithm that's meant to speed up spatial joins. And it's unique. This is going to be a unique research in the fact that no one's tried to apply touch yet to UAV data. The touch algorithm that was used for was relatively simplistic, and we're going to be trying it on a slightly more complex domain. As well, if we have time, we're going to do some stretch goals here of improving touch itself. What we're going to do at the end of the day is basically to test touch, which is this spatial join improvement algorithm using some hierarchical trees. We're gonna test that against the UAV data, and then we're going to test it against PostGIS without touch. So basically, PostGIS is going to be our code base, and from there we're going to apply touch to it. So the task is that the UAV will perform the flight, record these images along the way. From this, we will have to create data point clouds and put these into PostGIS. And so from this, we'll create photogrammetric projections from the point cloud data. And now we can rasterize that and use it for future flight planning. That's the end goal, is that this information will help us for future flight planning for things like takeoff, for things like where no-fly zones. It can also be used for things like surveillance, monitoring, exploration, that kind of thing. So we will basically need to, now most of the data, well, all the data I've already got from various UAV flights. So as far as recording images along the way, this part of the task for this research is not part of this research. That's It's just assumed that we'll have that. We will need to create the point data clouds. There's some well-known formulas for doing this, and I'll talk about that in a little bit. So the original scope for this included some queries and join optimizations. In the new proposal that I'm making now, I'm only going to cover joins. So the scope is basically this. I will build PostGIS. First of all, that's a little more complicated than it actually sounds. And that part's already done, but it involves branching the public source version of PostGIS, which is available on GitHub, for example. It involves branching that, building it. In this case, I'm going to be using Linux, and getting that to run. The second part is getting the UAS data into PostGIS. So one of my side jobs here is I work for Boeing, and so I've got some public domain data that has been made available by Boeing to actually use for UAS flight data. And this part is already done. This needed to be put into PostGIS so it can run simple queries on it, and that part is underway, if not done already. I've got most of the data into PostGIS, and I'm working on being able to run simple queries on it. So the next parts here that still have yet to be done is to perform our traditional joins, and then also the big part here is to create the join improvements using touch. Where I'm at with that is mostly the planning phase of that, and figuring out all the different aspects of that algorithm that need to be fixed, and looking at the PostGIS code and seeing where it needs to change. So basically there's going to be two branches. There's going to be one branch which is PostGIS untouched, no pun intended, and then there's going to be PostGIS with touch, which is the algorithms, and touch, by the way, is a in-memory spatial join performance enhancer based on hierarchical data-oriented partitioning, which was presented at a SIGMOD conference on management of data for the ACM in 2013. And then from this, we're going to obviously report results and recommendations, explain whether it's recommended that we use something like touch and hierarchical methods or not. And it's expected that we probably will see a speed up. The scope is our particular join tests. So, for example, this is a list of the types of joins that are available in PostGIS. Case of within and contains, basically A needs to be completely within B, so it's essentially an inverse of the ST contains, but basically the same thing. It just depends on how you order your parameters. So we'll be testing within as well. And so in the example that we have here, ST within is basically saying that the Jackson School geometry is within the Medford city limits geometry. And there's a full list on that site as well. So here's the problem domain. Basically, the UAV flight data will show certain footage of areas. For example, here's a footage of this area here. Oops. So this is footage of that particular area. And that footage is basically needed to be rectified with the actual representation we have for it in the data structure of the UAV system. So because what we'd like to do is ultimately we'd like to get a more accurate representation of that flight area. So in this part, we're basically, in this first part here, we're basically estimating the field of view of the UAV's camera. This can be used to generate a 3D pyramid, and from it we can estimate ground coverage. This is important because that way we know where to point the camera and how far away we need to point the camera, for example, and where we need to set the zoom levels and all that kind of thing. There'll be some PostGIS features like SV rotate or ST rotate to rotate the pyramid in position, and then we'll call the applicable select statements. So this part doesn't really need any joins. It's just getting it up to speed in terms of selecting the appropriate position of the camera. For this next one, once we've organized that UAS data correctly according to that pyramid, then we have to intersect it with the terrain model. So this is where the 3D intersection comes in. And so that flight data has to intersect with the terrain model that we might have gotten from, say, Google Maps or some other place. And so we're going to intersect it, and we're going to take the actual geometry of that into account. And the way we're going to do that is with point clouds. So for example, what we need to be able to accomplish is the images that are coming from the UAV flight data need to be converted to a point cloud. This is looking at it from MeshLab and seeing where all these point clouds exist. Once we have that point cloud information, we can generate an orthographic depiction in 2D map coordinates. This point cloud will be converted to 2D aerial representation, and we can use Voronoi polygons for this with a space filling approach to attribute these with certain colors from imagery and render them out. So again, this part is there's some well-known ways to go about this, and I'm just sort of using those methodologies, and a lot of this initial parsing of this data does not involve joins yet, but this is needed work that has to be done. That said, Voronoi polygons and the coloring of them will involve some joins, so this part needs to be tested as well. This will be one of our stages, and I'll show you the list of stages that are all being tested. This will be one of the stages of testing for the touch algorithm. We have to take care of proximity filtering in PostGIS, and that allows us to form points into Voronoi polygons. There's a k-nearest neighbor approach that I'll be using. So we can also use some joins such as STD within, but we're not focusing on that type of join, and therefore I'm just going to be using the traditional approach to it. But there is a touch approach that will be used for STD or ST intersects as well as ST covers. And both of those will be tested in our research. So the Voronoi polygons lead to a certain coloring of the polygon faces so that we get a representation of what the polygons are from the point clouds. So for example, here in the right, this is a rendering of using actual flight data that basically has, like, for example, the roads are blue here. The smaller road is red here, and that's just based on elevation. And then we have sort of the field as this grayish kind of color. And so all of these different colors represent a different Voronoi polygon that has been joined together. And that join happens as a cross join. So that's the Cartesian product of each rasterization as it's created, and we do a cross join on that. So that particular cross join is going to also be part of our testing. On the left side, you do see an orthographic map, but on the right, that's the one that's been created from the UAV data. That ST as raster is what's going to actually turn the polygons into a depicted rasterization onto 2D. So let's talk about spatial joining a little bit. The rest of this was sort of just prepping the stage for getting ready to do our joins, which is the real work of this research. So I don't want to take away too much from that. The other stuff that I've covered is sort of well-known ways of getting point cloud information into photogrammetric results. So in this case, let's say we want to find the intersections of R, with R1, R2, and R3 being our polygons, and S being S1, S2, and S3. So we want to report the results of joining up those R1s and R2s, R2 and S2, S2 and S3, and R3 and S2. So if you look at this, we see that R1 and S2, which is right here, are intersecting. R2 and S2 are intersecting. R3 and S2 are intersecting. We want the intersection of this because we want the intersection of the flight data with that terrain model that we have from the map service. And that map service, by the way, could be ArcGIS data, that kind of thing that actually comes in. So we can join that up. Then we will have a intersection of the color data with the generated Voronoi polygons, and we'll create a rasterization based on it. We cannot use relational joins in this because there would be no order of in the multiple dimensions. Therefore, we do end up having to use a spatial join, and PostGIS does this in a couple different fashions. It either uses an indexed or a non-indexed nested join loop is what it's called. The index approach can be R-tree, that's the most common, B-tree, geometry columns. We actually, in PostGIS, they actually currently use a nested loop hierarchical traversal. So it's, it looks like this, for example. This is the, so this is the nested loop hierarchical traversal with an R-tree index. So basically PostGIS uses an R-tree index, and then it does a nested loop hierarchical traversal over it. So basically, it has to have a priority queue first of this space, and we're going to add the roots to it, and then while the priority queue isn't empty, we basically find that pair, find the intersecting pairs underneath it. So that's why it's a hierarchical loop join, and then for each one of those we go through that loop. So for each one of the intersecting pairs inside of that, we go through the loop, get the intersections, and add any additional nodes that have been found to that so that they eventually go through here and do the detection. So the way this works is the nested loop join looks at each pair down to the leaf nodes. So for example, if another set of data exists, say S with root node of S1 and S2, then we would see that we would join up S1 and R1, and then S1 and R2, S2 and R1, and S2 and R2. So basically that join up stage is where there's duplication. Each of S1 and S2, R1 and R2, each of those appears twice in this new R tree that we've created. So this is just depicting the R tree as it exists and showing that essentially we need to do a join at every level of these on down. And that's why we would end up with S1 R1, S1 R2, S2 R1, and S2 R2. So this indexing does take some time. PostGIS attempts to do that in memory. If it fails to have enough memory to do this, it goes external, which takes even more time. We'd like to keep it fully in memory instead of having to go external with it. So the idea is that perhaps we can save some space, and instead of having to join up, for example, all of this data together, so instead of having to join up and say S1 comes in and merges or does a join with R. So R and S are doing a join here. Instead of having S1 have to test against R1, S1 have to test against R2, and then S2 testing against R1, and S2 testing against R2. Instead of that, because what that's going to generate is, so this is R1, R2. There's an equivalent S1 and S2 in the other tree. So each of those has to compute it has to create a duplication and join up based on that. Instead of doing that, which is going to take quite a bit of space, we're going to actually do an in-place sort of memory solution for it that does not take all that space, and that's what touch is basically. So we'd also like to remove the requirement of creating these two indices that need to be had at every step, and optimize the type of tree used, removing that duplication of those nodes. And hopefully it will also be very fast to generate this as well as use it. So the main innovation in touch. Basically, there's a direct assignment of objects from the second data set to the data-oriented index of the first. So that way we don't have indexing overlap, or there's less, and everything is contained in a tree. So let's say we've got B. Let's say we've got B and A that are joining up. We're going to directly assign the objects from that second data set A into B, and then organize it from there. So at first you see, and I'll get into the details of this in a bit, but you'll see that the A nodes become leaf nodes of B. And from there we need to organize that index. So we're going to build a hierarchical tree as the support structure, and we're going to create an index data set A with it, and then assign objects from them into the tree T. So for example, in its first phase, it's going to build this hierarchical tree based on A. Each one of these is going to contain pointers to children nodes and what's called a minimal bounding rectangle as well. Then we'll have these pointers of objects, and each one will be either a pointer to data set A or B. And then we're going to basically use each leaf node to store entities that are within it. So you can see that, for example, the dashed lines are showing that enclosure. So the dashed lines are outside of the MBR of the nodes at the leaf level. And these dashed lines indicate that the MBR of the node encloses all the MBRs of its children. So this dashed line indicates that it encloses all of these, and this dashed line indicates that it encloses all of these. And likewise, if we broke this apart, we'd see that there'd be a dashed line here that's enclosing these. So basically, as the tree is built, A1, A2, A3, A4, A5, A6 need to be put under this set of Bs. And let me show another picture of that. So here's another picture of that. This is the data set A that's initially going to be built just by normal means of tree building and spatial representations. And then there's going to be leaf nodes on each one of these. So B is going to come in, data set B, and each one of these in B is going to be assigned to something in A. So for example, here we see that this is one of the A's, and it ends up getting this child, for example, from B. And these children are filtered out and given to A as well. And as I said, these objects are filtered out because they cannot safely intersect with any object from that actual data set A. So these will be not part of the intersection calculation. And therefore they don't need to be part of the tree. But these other ones have been added to A underneath as part of its leaf nodes. Like, for example, this one here, and this one, and this one, and this one. These all go under A in wherever is applicable leaf node. So there's 3 phases of this. First, build a hierarchical tree, then an index data set A with it, then assign objects into that tree, then compare the inner nodes of T to the leaf nodes to see where it's reachable from and put them in those leaf node positions. There's a couple algorithms here. I think I went through this in great enough detail. Assignment phase, join phase. And as I said, some of those will be filtered out if it's not possible to join them up. So our comparison here is that UAS is going to be run multiple times, and the results are compared across touch joins as well as traditional joins. And the groupings are going to be per join type, which is going to be visible in the results section. So we're going to test both of these with PostGIS. These are the types that I'm planning on testing. Voronoi, which does a calculation to get, and it's going to end up having some join information in it, as I covered. Point cloud generation has a within call to it. Coloring has an intersect call, and rasterizing has some join calls as well. So each one of these stages is going to be tested, which means that we'll have speed times for touch versus traditional in each one of these categories. So the expectation here is that we will have improvements in this new version of PostGIS that includes touch. A side product of this will also be that we'll get some nice orthographic maps from the generated flight data. That's sort of a stretch goal because it's not really needed for this research to rasterize those, but if possible, I'd like to be able to achieve that. This was their results from touch on other data sets. And we see that touch had a very low amount of time in execution compared to some of these other methods like pure archery, for example, was here. Here's where I'm at. So PostGIS source code installation, that is done. The branch code has been made, and we've got 2 branches now. And I've gone ahead and imported UAV data into the PostGIS database. So I'm working at making sure this data is sterilized and making sure we can do nice queries on it. And that's where I'm at now. So I'm sort of still at the traditional phase of it. And then hopefully that'll be done within a week. And I'll get over to the touch enhancements and then run the comparison studies. All right, thanks for watching this far. Oh, I should mention that this is my reference list, my working reference list. These are the ones that have been most helpful to me. Especially the touch in-memory spatial join by hierarchical data-oriented partitioning done by Nobari. And then there's also been some orthographic papers that are useful. Generalization of query execution efficiency on spatial databases. This one actually used Unity, a 3D game engine, for comparison of different performance from UAV images, so that was very applicable. And then some general PostGIS essential things like a book from Pact Publishing, and a few other things like an introduction to PostGIS and some Octree papers. This one's actually a duplicate. I'm going to delete that there. We already have that one. So thank you.